Hello everyone, my name is Russell John. I'm here today with my intelligent classmates. We are going to teach you about the problem from systems analysis, and more specifically, we are going to talk about the problem about the state equations, and we're going to teach you with the problem of representing it in terms of drawing signal flow graphs. At first, the process will help us visualize state variables. Later, we will draw signal flow graphs and then write alternative representations of a system in state space. So that's it. Let's start.
Good day everyone, I am Jade Mark Alforge, and in this video, I am going to teach you how to draw a signal flow graph from state equation. Consider the following state and output equations. So, how to convert this to signal flow graph? So first, let's identify three nodes for the state variables. X sub 1, X sub 2, and X sub 3. So, three nodes. 3. Also, identify three nodes to the left of each respective state variables as their derivatives. S x sub 1, S x sub 2, X sub 3 to the left of each respective state variables. Also, identify a node for the input Rs and another node for the output Ys. Then interconnect the state variables and their derivatives with the defining integration 1 over S. So let's feed all these signals to S x sub 1. So from x sub 1, there is a signal of 2. And from x sub 2, there is a signal of negative 5. And from x sub 3, there is a signal of 3. And from the input R, there is a signal of 2. So, and the second equation, we have to feed all the signal to x sub 2. So from x1, there is a signal of negative 6. And from x sub 2, there is a signal of negative 2. And from x sub 3, there is a signal of 2. And from the input Rs, there is a signal of 5. So now, the third equation. So we feed from x sub 1, there is a signal of 1. And from x sub 2, there is a signal of negative 3. And from x sub 3, there is a signal of negative 4. And from the input R, there is a signal of 7. So from the output, there is a signal of negative 1 and negative 4 from x sub 1. And from x sub 2, there is a signal of 6. And from x sub 3, there is a signal of positive 9. So this is the signal flow graph of this state equation.
Hi, I'm Marley Gamayon, I'm going to teach you another example in drawing signal flow graph from vector matrix form to state equation.
In order to get the signal flow graph of this vector matrix form, you may convert this into a state equation for simplicity, or not if this form is convenient to you, just leave it as it is. First, identify the three nodes for the three state variables. We have x1, x2, and x3. Second, identify the three nodes to the left of each respective state variables as their derivatives as sx sub 1, sx sub 2, and sx sub 3. Third, identify a node for the input, which is r of s. And for our output, y of s. Fourth, then, let's interconnect the state variables and their derivatives with the defining integration 1 over s. From x sub 1 to sx sub 1, there's a signal of negative 2. Then, from x sub 2 to sx sub 1, we have the signal of 1. Okay, for the next equation, we have from x sub 2, we have negative 3 to sx sub 2. From x sub 3 to sx sub 3, there's a signal of 1. From x sub 1 to sx sub 3, we have a signal of negative 3. From x sub 2 to sx sub 3, we have a signal of negative 4. From x sub 3 to sx sub 3, we have a signal of negative 5. And lastly, we have r to sx sub 3. And for our output, we have x sub 2.
Hi, I'm Ivy Milagahit. I'm going to teach you the alternative representation in state space, particularly the cascade form.
So given a transfer function, draw its signal form. So we have an equation of 24 over quantity of s plus 2, quantity of s plus 3, and quantity of s plus 4. So with this equation, we can expand this into this form. So 24 times 1 over s plus 2 times 1 over s plus 3 and times 1 over s plus 4. So with this equation, we can make a block diagram in a cascaded form. Is to convert the signal to nodes. This will be the sx3, x3, sx2, x2, sx1, and x1. So next is to convert the system into branch. Interconnect the state variables and their derivatives with the defining integration 1 over s. So from the rule of simplifying back diagram, we can actually say that there is a feedback from x of 3 to x of 3 of 2. This also applies to x of 2 to x of 2, which is 3, and x of 1, which is 4. And we will connect the remaining nodes with the branch with a value of 1.
What's up everyone, my name is Matman Ernie Viewbal and I'm going to teach you another alternative representation in state space, and that is in parallel form. So this is the parallel form. Given a function, draw its signal flow graph. So we have given a function of 24 over s plus 2 times s plus 3 times s plus 4. So the previous form was arrived at by cascading the individual first order subsystem. So in parallel form, this is derived from a partial fraction. C is the sum of the three terms and the R of S are the inputs. So first is convert the signal to nodes in parallel form. So first is to identify the three nodes for the three-state variable x sub 1, x sub 2, and x sub 3. Also identify the three nodes to the left for each respective state variable as their derivative as x sub 1, as x sub 2 for x sub 2, as x sub 3 for x sub 3. Also identify a node for the input R of S and another for the output C of S. And then interconnect the state variables and their derivatives with the defining integration 1 over S. So the next step is interconnect x sub 1 to x sub 1 with a feedback of negative 2. Also in x sub 2 and s x sub 2 with negative 3. X sub 3 to Sx sub 3, negative 4. From the input signal R of S to Sx sub 1, there will be 12 from Rs to Sx sub 1. And then from the input signal R of S, there will be negative 24 to Sx sub 2. From input signal R of S to Sx sub 3 will be 12. Since C of S is the sum of the three terms, we'll just connect them with a branch.